And can I just say I can quiz on anything else I want in chapter 5 in any order? Right? So Simpson's rule, improper, partial fractions, and then I'll give you a warning before we do area between curves, disk method, shell method, right? And this way I'm going to be able to quiz on everything, which is cool. Not that you would like it, but I think it's good. All right, so we're looking at 6.4. And we're talking about arc length. And I want to go to my final formula for arc length, and I'll see if I can explain it to you, okay? So here's my arc length formula. What do you see in that formula? Yes, a derivative. Good. What else? Hypotenuse. It's a hypotenuse here. So I've got something squared plus something squared in a square root. It's a hypotenuse. So that's where my derivation is going to come from. Okay, but we want to look at this particular formula first. So we're talking about arc length. Now think about it. We got an integral to give us an area. That's a two-dimensional object, right? We got an integral to give us a volume. That's a three-dimensional object. When I get arc length out of this, that's a one-dimensional object. It's going to tell me 3 feet. That's how long the arc is, right? So it's crazy that the integration can represent all these different dimensions, and it will do the same in your field, right? Particularly physics, if I'm thinking about force or work, something like that. The integral is going to give me that. Are we taking physics for engineers?
Yeah.
Next, what is it? What's the course you signed up for?
161.
161 is the first of it.
Okay, I haven't signed up yet.
Yeah. And so, but they ask you to take that after Calc 1 because you're going to be doing derivatives and integrals in it, right? So anyway, arc length. So what do I have? I have the length is the integral from a to b of the square root of dx dt, quantity squared, plus dy dt, quantity squared, dt. Now this is parametric. You can tell by the parameter t. Time is usually our parameter, right? Talking about where a particular insect is flying with respect to time, that type of thing. But of course, if x equals t, right, dx equals dt, right? And dx dt equals what? 1. So this thing could turn into the square root of 1 plus y prime squared dx. So those are the two I want you to have on your formula sheet. Right, do you agree with that? If x is t, if it's that simple parametric equation problem that I have, right, you agree? dx dt is 1. If I take the derivative of x, I get 1, yes? And then dx is dt, same thing. So I just converted everything, right? So these are the two. This is with the parametric equations.
Only get that second one when x.
Exactly. When it's already a function of x, is the same as saying x equals t. But this one you could just say y equals f of x. You don't have to think about it in terms of the parameters. All right, let's just do a problem right off the bat, and then I'll see if I can come up with the explanation for you of what the hell's going on. How did we generate this formula, right? So we can start nice and easy. Let's start with number 3. And you see here I'm in a function of x, so I don't need the parametric version of it, right? So y equals sine of, I want to find how long that curve is from sine from 0 to pi, right? So our first problem is going to be y equals sine of x from x equals 0 to pi. Right, and I'm asking how long is the curve? Yes, you're understanding what I'm asking. I just want to know how far that is. Whether it's in feet or inches or meters or whatever, who cares? What's the coefficient is what I'm asking, right? So I have the integral from 0 to pi of 1 plus y prime quantity squared dx. And so what's y prime, first of all? If y is sine of x, right? Y prime is cos of x, right? Positive. And then y prime squared is cos squared of x. So my length is from 0 to pi of the square root of 1 plus cos squared of x dx. Now this one, I can't quite do this one yet. I don't have anything nice I could put in for 1 plus cos squared. So they're just asking me, right? They're just asking me, I think in the book, to do it on use a calculator. So we're going right to Desmos here, right? So I'm going the integral, int, from 0 to pi of the square root of 1 plus cos squared of x, get out, dx. So about 3.82. Just we're finding one particular length, right? This one we couldn't do the integral of. The one I'm going to give you, of course, you'll be able to do the integral, right? Let's do number 11. Yep. So we have to figure out, right? We have to figure out this particular piece. We want to find the arc length. What's it telling us? Number 11. From 1 to 2, it's giving us the bounds that it wants, right? From 1 to 2. Yes, you see my screen here? Number 11, 1/4 x squared minus 1/2 ln of x from x equals 1 to 2, right? Find that arc length. So we need y prime. Who's got it? So x squared, derivative of x squared is 2x, but over 4. And then derivative of ln is 1 over x. So there's my y prime. Now, I find it's often easier to work on that piece outside of the radical, right? Noah, are you okay? it's often easier to work on that particular piece outside of the radical. So I'm going to work on that, do some side work here. I like to get an LCD first. So I get x squared minus 1 all over 2x. And then I'm going to add 1 to it, right? Oops, I got to square it. And I think that's where I'm going back into my integral. Right, once I get that squared, because then I know I'm just doing an LCD here. And this is, if you remember in Calc 1, all the hideous algebra? It shows up every now and then in Calc 2. In this particular one, it's showing up. But at the end, nice and simple, x squared plus 1 all over 2x. Right? We're trying to get you problems that will have a nice square root when we're doing these. And then it's just boring out for the rest of it. So let me see if I can explain what's going on with the formula, okay? What I'm going to do is take a curve, right? So you see my curve here in blue. Can you see it, Noah, at all? Yeah, and then I've got a bunch of hypotenusae in pink. So just from P0 to P1, you can see a height of y and a base of x, and then that hypotenuse, right? And I know that that hypotenuse length is square root of the base squared plus, right, plus the height squared. So what I'm doing is I'm adding up that width delta x squared, right, plus that height delta y squared. If I turn it into a parameter, I know that any delta x, right, or the slope of that hypotenuse is delta x over delta t. I can kind of think of that. And then, of course, as so there's my dx dt happening, right? But I need it squared, of course. So this thing is telling me, okay, I know that delta x is some derivative times delta t, right? And delta y is same thing, some derivative times delta t. And then I make my substitution there. You can see that right there on this middle line, right? I've changed my delta x into that derivative times the delta t, and then squared, right? But then I can factor out that delta t, right, squared, and it comes out of the radical as a delta t, which, and as I make my hypotenuse smaller and smaller, right, my hypotenuse, that delta t becomes the dt, right? So there's our piece. I mean, I don't think I need to say more than that. I would ask, if you're thinking about theoretical physics, you're in math, you're going to take a look at that a little bit closer. Okay. Let's do one with a parameter. Almost the same one as before, number 20. Let's do the length of the loop of x equals 3t minus t cubed and y equals 3t squared. So of course we want to look at that on Desmos first. So this is 6.4, number 20. So we want to take notice of right, where our x's are moving, and then of course that because we're going to be doing this in terms of t, we want to find the values of t as well. Okay, so Desmos, you got it already? Parametric, 3t minus t cubed, comma, 3t squared, I like to put in the slider A on one side and just see what happens as I build it. That's a pretty, there's my loop, right? So there's my loop, and I'm just basically guessing at the parameters. I did from 0 to A, and it just went away, and it didn't create a loop. So I think I have to go backward, right? But as I'm watching this, right? As I'm watching this, I can see where my loop is created, and where my loop ends. And what are the x values on both of those? 0. So I'm setting that x value equal to 0 to get my t values. X equals 0 implies that, 3t minus t cubed equals 0. So 3 minus t squared. And so it looks like t is 0 or t is plus or minus square root of 3. So similar, right? So also similar is I have symmetry. So I can decide to do half of it or I can decide to do the whole thing. It should be pretty clear when the t is 0 is. When I look at that graph, it should be pretty clear when the t is 0 is at the base of that loop, right? So my whole loop should be going from minus rad 3 all the way to rad 3, right? So we're getting the length from minus rad 3 to rad 3 of the square root of, I need the derivative of each but squared, right? So 3 minus t squared, 3t squared, squared, right? There's my delta x squared. Let me not save paper. So dx is what? 3 minus 3t squared dt. And dy is 6t dt. Oh, we don't need the dt, sorry. I'm actually doing this version, right? And then I need to square each of those. Again, I'm thinking it's better for me to do that on the side than anything else. So I'm working on that piece on the side. And it's always, if I'm going to get you to do one of these only on, without a calculator, it's going to have to be something that's going to work out nice in a square root. And of course, this one is simple as all. Right, the square, it just will cancel the square, right? units. Whatever the units are, right? I made a mistake somewhere, but not much. Did I make a mistake on a coefficient somewhere? T cubed over 3, and then t, right? You get the same thing as me, or get something different?
Got half of that.
Yeah, that's what I'm showing. I just made a mistake somewhere. Do you see my mistake? You have the same antiderivative as me?
Yeah.
All right, then I made a
And
mistake.
I did 2 times.
Yeah,
uh,
yep. 2 times because of the symmetry.
Yeah.
Yeah.
0, 3.
Yeah.
Oh, the negative root 3,
Yeah.
the third, that's gonna end up negative.
Yeah, but because you're f of b minus f of a, the negatives all cancel.
Negative.
Right.
Root 3 squared plus 3 is 6. I'm done.
Oh. Thank you. That's my mistake. Thank you.
You found it.
Yay! Well, I got good news for you. Normally, right now, we would be quizzing, but because there was some confusion on what quiz I was giving,